Recording has started. So, welcome to an extra session of this course on parameterized algorithms. So, in today's session, the plan is to look at two algorithms, parameterized algorithms. So, as discussed and as proposed by Mr. Goel, that we'll once look at a problem which uses kernelization. I mean, the algorithm parameterized algorithm uses kernelization, and another algorithm for another problem that does not use kernelization. So first we'll start with the first problem. So let's start with our favorite problem, which is a vertex cover problem. So we have seen this before, but for the sake of completeness, let us see it once again. So in the vertex cover problem, the input is a graph G, and in the parameterized setting, there is a parameter, integer parameter K. And the objective is to, let us say, G is composed of vertex at V and it's at E. So the objective is to find or select a subset of the vertices such that all the edges are covered. So in this case, covering means an edge is said to be covered if at least one of its endpoints is part of the vertex subset that you have selected. So additionally, you would like that you don't select more than k vertices in the parameterized setting. Okay, so the problem is NP hard, so we cannot expect a polynomial time algorithm in N. But what we would like to see is an algorithm uh, no polynomial time algorithm. We would like to see an algorithm that runs in this much time. So polynomial in N, but potentially exponential in K. So f of k is any function of k, and as long as k is small, if k is not a function of n, so if k is constant, then you have a polynomial time algorithm. All right. Okay, so we have seen a couple of algorithms for this problem. So let us look at the algorithm that uses kernelization. So what is the meaning of kernelization? Kernelization basically means that you reduce. So kernelization is a procedure. It's a process that takes the input and obtains a reduced input. Okay, so from a graph which is given to you, obtain another graph in this case, and potentially the parameter can also change. So k can become k dash. But what will happen is in the reduced graph, you will be able to solve the vertex cover problem quickly or any problem quickly. So the reduced graph, we would potentially prefer to have size polynomial in k. So if we can manage to show that from a graph which was of size n, so let us say n was the number of vertices, you obtained a graph whose size is polynomial in k, and now that you have a manageably small graph, then you can use brute force and you can achieve a running time which is of this form, some function of k times n to the power constant. So that is the whole idea of kernelization. So we say that a problem admits a polynomial kernel if you can do such, if you can find, of course, this procedure kernelization has to be running in small time. So the runtime of this kernelization procedure should also be at most this much.
So then, what is the difference in between the kernelization and the fixed point tractability? I mean, is this the case that fixed point tractability is a part of the kernelization among other possibilities?
Yes. So fixed, what did you say? Fixed parameter tractability, right?
Yes, yes, yes.
Yes, 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 yes. So fixed parameter tractability means a problem is said to be fixed parameter tractable if the running time of solving the problem is of this sort. So one of the ways of obtaining a fixed parameter tractable algorithm is kernelization. And as we are going to see that there are algorithms which are fixed parameter tractable and does not use kernelization. Kernels do not exist, but still with some other techniques, fixed parameter tractable running time, this kind of running time is achievable.
Okay, okay.
So if we are lucky, then a kernel might exist, a kernelization procedure that requires reasonably small amount of time can achieve such a reduction. So when the kernel exists, when the kernelization algorithm is possible, then the algorithm becomes very straightforward and does not require too much of heavy machinery. For example, in this case, so kernelization, as I said, is nothing but uh, a set of reduction rules applied on the input. So the graph needs to be reduced. The graph needs to be made smaller by making some clever observations. Okay. So the problem that we are interested in is vertex cover. So suppose I'm looking at a graph, and of course I have been given a parameter k, and I have been trying to see if vertex cover of size less than equal to k exists. Okay. So what rules can I apply to reduce this graph into a smaller graph? So for example, suppose there are some vertices which have degree 0, that is these vertices are isolated. Then can these vertices be part of the vertex cover?
No.
Yes, because they are not covering any of the edges. They cannot be part of any vertex cover. So we can reduce the graph by deleting these vertices. So one of the reduction rules, so reduction rule 1 is delete all isolated vertices and obtain the graph G dash, and the parameter k remains the same. So you still have k budget. You can still choose at most k vertices in your vertex set after deleting these isolated vertices and obtaining the reduced graph G dash. So that is one simple observation. So let us say you have a degree 1 vertex. So you see that, okay, there is a vertex which is like this, like this. Oh, let's take a different color. So there is a vertex which is degree 1. Then can you apply some rules?
So here, this vertex will always be included uh, because to cover all the edges and not necessarily because yeah. So, but if we have a vertex of the degree one, then whether this vertex so yes, because its degree is vertex one, it will never be included. Why so? It
Yes.
can be ignored to some extent because it will be connected to other vertex, and which might be having better chances of connecting to the other edges.
Yes, 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 yes. So one can write another reduction rule. One can say that if you see a degree 1 vertex, then do not take it, take the other end of the edge. So this is, let us say, U and this is V. So if you see U is connected to V, where U is a degree 1 vertex, take V, because V might be connected to other edges, other vertices. So V is potentially uh, uh, able to cover more edges than U can cover. So if you see a degree 1 vertex, one can write a rule that, okay, that take the neighbor of a degree 1 vertex, because that potentially can cover more edges. But if V was also degree 1, then it is also covering only one edge, but potentially there could be more edges it is covering. So if you take the neighbor of a degree 1 vertex, then what happens? You get another graph G dash, and since you have already taken a vertex in your vertex cover, so now your budget is less. Now you are not allowed to take k more vertices in your vertex cover. So your budget gets reduced by 1. Okay. That is one reduction rule one can think of.
So I have something to say here that instead of reducing the budget, say by one, it will get reduced by some even quantity because there would always be the even number of the vertices having the odd degree.
No, so what is the meaning of budget? Budget means how many vertices you can include in your vertex cover. So initially you had the budget of k, that you had the liberty to pick at most k vertices. Now after doing this reduction step, you have taken one of the vertices in your vertex cover. Which is that vertex? The neighbor
Yes,
of u.
yes. It's clear. But then, yeah. So. So I mean to say that there would always be the even number of the vertices having the odd degrees. So if we find even a single, if we find a single vertex of the degree one, there would always be the another vertex also.
That is true.
Yeah,
That is
yeah.
true. Uh, that I completely agree. Because the sum of degrees is even. So the number of odd degree vertices is even. But more than what, we are looking at those vertices which have degree 1. That is one way of writing a reduction rule. So remember that reduction rules people can think of. So for example, somebody may ignore this reduction rule. Depending on how it will help you in your analysis. After the kernelization, you have to do the analysis that, okay, after I have applied these reduction rules, now I'm left with this small graph, and this small graph is manageable. So how you will define the reduction rule is completely up to you.
Can I include one more rule that the vertex which has got the highest degree would always be included in the
Yes,
vertex cover. So, but
absolutely
uh,
true. Yes, go ahead.
but even I am doubtful that whether this will always be the case because if we consider a star kind of the situation, in that thing it is okay. But
Yes.
if we have, so I cannot think of, probably there could be a violation of this thing wherein despite having the highest degree of a vertex,
Mhm.
we choose to, include some other vertices. There could be a contradiction. I'm not sure.
Yes, so we can, whatever you are saying is definitely in the right direction. Your intuition is absolutely correct. So slight modification is required. So instead of saying highest, we'll say high degree vertex. Of the settings of this pencil needs to be changed. So high degree vertices are more beneficial because they cover more edges. So high degree vertex, but we have to specify what is the meaning of high. So I will say that vertex of degree k plus 1 or more is called a high degree vertex. Okay. So now look at this vertex. Let us say there is a vertex. Now let's look at this figure only. So in this figure, this is okay. Let's say there's one more edge like this. Okay, I'm looking at this vertex, red vertex. Okay, red is already used now. Let's take another color. Looking at this red pink vertex. So what is the degree of this pink vertex? 5.
Five. One, two,
So
three, 5.
let us say k is equal to 4, and this is a vertex you're looking at whose degree is more than 4. Now, if you do not take this vertex in your vertex cover, then these 5 edges, how will you ensure that these 5 edges are covered? These 5 edges have to be covered. So you have to take the other endpoints. If you don't take this guy, which is degree 5, then you have to take the other endpoints, all of them. Yeah. So
Yes.
you're already failing. So your objective was to use at most k vertices. K is 4, but you already see that if you don't take this degree 5 vertex, then you have to take this other 5 vertices which are neighbors to this degree 5 vertex. So that you cannot allow. So therefore, whenever you see a vertex of degree k plus 1 or more, you should definitely pick it. Does that make sense?
Yes.
Yes.
Yes. And yeah.
And you have to, of course, update the parameter. So you have taken a vertex. So your budget has decreased by how much?
So now, by the depending upon the degree of the vertex, so k minus the degree of the vertex, k minus k. So if the degree is k plus 1, this vertex has definitely been included, and then we are left with k minus 1. K minus 1, yes.
Yes. Yes. So if you have started with a budget of k, you have picked a vertex. So you have to reduce the budget by 1.
Yes.
So is there anything else we can think of? So after doing all these steps, we will be left with one reduced graph. We'll have a final reduced graph, which is G dash, let us say. Then we have to argue. So we had seen what is kernelization. That size of this graph is polynomial in K, that we should argue. So you have to argue. Then only we will be able to say that the kernelization is successful. So, so it turns out that even with only 2 rules, this high degree vertex rule, let's call it rule 3, and this deleting isolated vertices, these 2 rules, with these 2 rules alone, one can find a reduced graph G dash whose size is polynomial in K. It is so magical that the dependence. So initially you had n vertices, but after doing these 2 rules alone, you are reducing the size from order n to order k. I mean, k to the power c, let us say, some constant c. So polynomial in k. So this is going to be the size of this reduced graph, but we have to argue it. Okay, so before we argue that, let us believe that after doing these set of reduction steps, rule 1 and rule 3 we have applied, we are able to manage to show that, let us say, this reduced graph has order k square, let us say order k square vertices and order k squared edges. Then how shall we solve the vertex cover problem on the original graph? So first thing is, we will argue that how this is true. So suppose that we have been able to manage to show this. Okay. So two things are possible. So either you run out of budget, that means you. So what is the meaning of running out of budget? So if you applied rule 3, then you have taken a high degree vertex and then you have reduced the budget. So if there are so many high degree vertices, then you may run out of budget. And what is the meaning of running out of budget? Does it mean that a vertex cover of size k does not exist?
Yes. So if we go beyond the budget, then the vertex cover of that size does not exist if we have exhausted all the possibilities and tried all possible ways of computing the vertex cover.
Yes. For example, let's take a concrete example. Consider a clique that is a complete graph. Clique means complete graph on n vertices. Okay. And suppose you are given a budget k, which is equal to n minus 2, let us say. So what is the vertex cover size for a clique on n vertices?
So that would be 1 because every vertex is connected to every other vertex.
Yes. So between every two vertices, there is an edge. So let's say a concrete example. Here is a clique on 4 vertices. So how many vertices you should take in your vertex cover? You have to cover all the edges. There's so many edges.
So yes, so every vertex is connected to every other vertex. So if I take vertex number 1, so it I mean which edges are going to be covered? 1, 2, and then 3. And yeah, so if I take the vertex number 1, then the edges 1, 2, 1, 3, and 1, 4 are getting covered. Now which edges are remaining? So I need to include, say, one more, that is 3. 3 vertex should also be included. So yeah, so every vertex is connected to every other vertex. So here I require 2. I mean, two would be the size of the vertex cover. Minimum I would be requiring two
Which
number
are the
of
two
edges.
vertices you will take? 1
But
and 3.
still, but still one is remaining, and what is that? The 2, 4 would be remaining then. So I'll have to include one more.
Correct. So if you do not include 3 vertices, then 2 vertices will be left. These 2 vertices also have an edge between them. That edge will remain uncovered. So what happens in the general case? Suppose you're looking at a clique of n vertices. Okay. So in this case, how many vertices you must select?
So since there would be a large number of the edges this time, so n minus 1 seems to be okay.
Yes. Because if you do not take n minus 1, if you take n minus 2 also, then the two vertices that you have not picked, among them there is an edge which will remain yet to be covered. So you are forced to take at least n minus 1 vertices to cover all the edges. So therefore, if your budget is only n minus 2, a vertex cover cannot exist of that size. Okay. So you will keep deleting. So you apply this high degree vertex rule. So you see that every vertex has degree n minus 1. So you keep deleting it. And after deleting n minus 2 vertices, you will be still left with 2 vertices. And then you will conclude that, okay, this is not the graph for which I can find an n minus 2 sized vertex cover. So this is the no instance of a vertex cover. So that means if your budget is exhausted by applying the reduction rules, then you can simply conclude that this instance is a no instance. It does not admit a vertex cover of size k. That is the first conclusion. So after doing the reduction step, you should not be out of budget. So you can have zero budget, but you should not go to negative budget. That should not happen. But if it so happens that you did not exhaust the budget, you exhausted the budget, but you did not violate it, you did not overflow the budget, then what you have to check? Then you have to check that how many vertices and edges are there in the reduced graph. And if you see that the number of vertices and edges in the reduced graph is small, some polynomial in k, let us say k squared vertices and k squared edges are left, then how much time do you require to find whether a vertex cover of size k exists or not in this reduced graph?
So that will depend on that to what extent the number of edges are being reduced after including a vertex as the part of the vertex cover. So say if I include a vertex as the part of the vertex cover, then to what extent I am reducing the number of the edges in the graph?
Correct. Correct. So that is one by one you can check that, okay, I have, let's be more concrete. Let us say that after doing all the reduction steps, you have 5 k squared vertices in the reduced graph. And some, let us say, 10 k squared edges in the reduced graph. Now you have some graph. You know that the size of the graph is order k squared. Now you're saying that, okay, I am going to take a vertex. So some of the edges which are incident on it, all the edges which are incident on it are covered. So I'm going to do this iteration and I'm going to find it out. But how much time will you take in the worst case to check whether there exists a vertex cover of size k? How much time can take in the worst case? If you're being brute force also, you need to check 5 square, choose k possibilities only.
Yes, and this entire thing need to be multiplied by a factor of say 5k square by a quantity of 5k square. Because if I apply the brute force here, these many possibilities will exist, and further I need to check that whether this indeed is a
Yes.
vertex cover or not. Yeah.
Yes, some order k squared extra time will be required. So many candidate possibilities plus so much time. But even then, this is a polynomial in k. This is a polynomial. This is no dependence on n. Okay, I'm not saying sorry, why am I saying it's a function of k. It could be an exponential in k. In fact, it will be exponential in k, 5k squared to the power k. So, but it is a function of k. So you know that
I
after
have a doubt.
applying,
Yeah, I have a doubt here that whether the number of the possibilities indeed would be this much, because if we go for the brute force and if we are having 5k square number of the possibilities, these many vertices, for every vertex we would be having two possibilities. Either I include this as a part of the VC or not include as a part of the VC. So there would be 2 raised to the power 5k square number of the possibilities.
no, so you are not interested in checking those vertex covers which have size beyond k. So what you are suggesting is could lead to a vertex cover of size 5k square also if you take all the vertices. So we want to limit ourselves. We are only interested in checking, in verifying whether there exists a vertex cover of size k. Beyond k, I
Oh,
am not interested.
yes. Yeah. Now I understood. Yeah.
Yes. So this is again going to be how much? This is going to be, let us say, I'm giving a small. So let's say 100 choose 10. So how much that is going to be? So could be 100 to the power 10 or something like that. So this is going to be 5 k square to the power k or something. But whatever it is, this is a function of k. It is independent of n. So if you have been able to do the reduction in some function of k time, then verifying whether there exists a vertex cover of size k, that would also take some function of k time. So you are not going to violate running time beyond this. So your running time is not exponential in n, that you can ensure. So all you are left to do is argue that this reduction is going to give a reduced graph of size order k squared. All that is left to be argued. Because beyond that, once you have got such a small graph, then this verification can be done in some function of k time. So we will now focus on this part. All right. So we're going to focus on rule 1 and rule 3, and we want to argue that after all these rules have been implemented exhaustively, then the number of vertices and number of edges is only so much. So this
Yes.
part is simpler. Number of edges part is simpler. Let's do this one first. So So how does the reduced graph look like after you have eliminated all the high degree vertices? You have eliminated all the vertices of degree k plus 1 or more. Now you know that in the reduced graph, each vertex has degree at most k. Okay. So you want to argue that the number of edges is this much.
Yes, yes. So we can take the help of that equality. Sum of the degrees of the vertices is equal to the twice of the number of the edges. So if the degree of every vertex is say k, then k into say the number of edges is e. I mean, what conclusion can we draw? I mean, so how to draw this? That there, if the maximum degree of a vertex is say k, then there would be order of k square number of the edges.
Yeah. So uh, so if the number of vertices are also k, then you would have been done, right? S-
Yes. Then
But
it can be done because then their maximum number of the edges there would be of the order of say n square, and if n itself is an order of k, so then it
hmm,
would be of the order of k square.
yes. So now if the number of so yeah, so I have to say one more thing that uh, so we want to say that after the reduction is done in the final reduced graph, if there are less number of so many vertices and so many edges, then there is a vertex cover of size at most k. Okay. So so that is our next reduction rule, that if we do all these reductions, and after that we count how many vertices are there in this graph and how many edges are in there in this graph. If the number is sort of like this, then we will be able to say that the vertex cover size is at most k. So I will write down the lemma, then I will prove it formally. So if g comma k, that is the original instance, is a yes instance, that means it contains a vertex cover of size at most k, and none of the two reduction rules. So one reduction rule is uh, delete all the isolated vertices, and the other reduction is delete all the high degree vertices. Let's say only two reduction rules we have applied. If the original instance is a yes instance and none of the reduction rules is applicable to G, that means so I mean, so let's say G dash. So we are going by G dash. So after we have done the reduction, then we are getting G dash. So after we have done the reduction, then none of the reduction rules are applicable to G dash. Then the number of vertices in G dash is at most k squared by k squared plus k, and number of edges in G dash is at most k square. So if we are able to prove this, then we have an algorithm that runs in so much time and reports whether the original graph has a vertex cover of size at most k. So is the
Actually,
lemma
what's the
statement?
yeah, yeah, what's the meaning of this lemma? Can you summarize its importance again?
So so after we have done the first reduction rule, on the original graph, then the graph does not have any isolated vertices.
Yes.
And after we have applied the second reduction rule, then the graph does not have any high degree vertices.
Right.
Okay. So then we want to prove that after this has been done.
But Siddharth, like after applying the second reduction rule, then we
Yes.
again might end up with some isolated vertices. Although
No,
the
no. Exhaustively
right,
we will apply. We'll keep applying.
yeah, but the second reduction rule we have to apply just once, like
The
for all
second
the
reduction rule.
vertices.
Yes, if already you have deleted,
Hmm.
removed all the high degree vertices, then it cannot generate any more
Yes,
high degree vertices.
yes.
Okay, so now, so what is the importance of this lemma? So the lemma says that if the graph has vertex cover, so let us take it, take a concrete example. So if the graph is more like a clique, it's very dense, then you give a number k and ask whether it has a vertex cover or not of size k, then it is less likely that it will have a vertex cover of size. But it is, if it is more like a star, if it is more like a star, and if you give a number k, so if it's a sparse graph, then there is a higher chance that it will have a vertex cover of size k. So the lemma says that if the graph is more like a star, if the graph is an yes instance and admits a vertex cover of size k or less, then after applying these two reduction rules exhaustively, you will end up with a very small graph. You will end up with a graph whose size is only so much.
So I have to say something here at this point. So even if we apply the rule number two, we are not going to reduce the number of the vertices or the degrees of the vertices by any amount. Like say if we apply the rule number two, we are not going to generate more vertices of the degree one. The reason being that by including, I mean, by applying the rule number two, we are just saying that that vertex will become the part of the vertex cover, and the degree of all the vertices, everything would remain unchanged. And those vertices whose degree is one have already been, I mean, have been removed from the problem. So by applying the rule number one, we are removing the vertices possibly, but by applying the rule number two, we are just including that vertex of the higher degree as a part of the vertex cover, and the degree of other vertices is not going to be changed.
No, so the meaning of applying the reduction rule is the following, that when we pick a high degree vertex for inclusion into the vertex cover, this vertex as well as the edges incident to that vertex are deleted from the graph to get a reduced graph.
So, but then we won't be, I mean, should not be deleted ideally, because everything would remain at its own place only. The only thing is that now those edges have been marked by something, and those edges won't be considered anymore. And so that they, I mean, this does not affect the degrees of the other vertices. My point is, so that I mean, the degrees of the other vertices after including this high degree vertex as the part of the vertex cover should not be changed.
Okay. So you are
Because if we,
suggesting.
yeah, because if we delete the things, then the problem instance as a whole will get changed, and the degree of many vertices, I mean, will get changed also. And then, I mean, what could be the meaning of applying the rule number one and the rule number two exhaustively won't make much sense, I think.
No, no, but we are when we are removing that vertex, we are actually putting it into the solution, right?
Yes,
Because
yes, yes.
we have reduced the our budget by one after every application of the third rule.
So yes, so when we include a high degree vertex as the part of the solution,
Hmm.
all the edges which are incident on that high degree vertex and as well as through the other vertices would remain at their own places only. So that the degree of the other vertices is not being changed. However, we can mark them with something, with a flag kind of the thing, that okay, these edges have been covered, and should not be considered further while formulating the vertex cover, I mean to say.
I think we should be deleting them.
So
There is
basically,
no harm in that the other vertices have their degrees getting reduced,
so
because now the
yes,
number of edges that we want to cover is also
yes. So if we change the degrees of the vertices, then we'll have to apply these rules again and again. We'll have to apply the rule number one again and again,
That is
because
true.
then we can get many more vertices of the degree one in the
that is
code.
true. So I think if we apply rule 1 once, then rule 3, I mean this removing high degree vertices, then we once again need to apply rule 1, but that is all I
Yes.
think.
The rule 1
Yes,
may be required again, but we will
yes,
keep applying rule 1 and rule 3 as long as it is possible to do so.
yes. Because when the degree changes, very little is guaranteed. I think. I don't know.
No, guaranteed is like, so you are saying that in the reduced graph, we are solving the problem, but in the original graph, we may not solve the problem. Are you concerned about that? That the equivalence of the problems being solved in G dash with the problem being solved in G is not holding?
Yes, so I mean to say, because then many more, I mean, vertices of even the higher degree will get generated. Because if the degrees are getting changed, then quite possible that one vertex is having the degree, say, 3. And after the deletion of the edges, say, it may so happen that its degree all of a sudden may become, say, 2. Uh, okay, yes. So there is a small difference. I mean, but deletion. If we allow deletion, then the rules should be applied multiple times. Uh,
Exhaustively, yes, as
yes,
long as
and
it is applicable.
yes, and if we do not allow the deletion, and if we use some flag kind of the thing, then probably I mean applying these rules once in one iteration would be sufficient.
Yeah, I mean, so uh, as per the algorithm, they do the deletion exhaustively. So when they pick a high degree vertex for inclusion, for example, if you pick in this graph, let us say this vertex 2, then you are already sure that these edges which are incident to 2 are covered. So then you are left with solving the problem on the remaining reduced graph. But of course, now your budget has decreased. Now you cannot have budget as k. So as per this algorithm, the meaning of application of the reduction rule is taking a vertex which is of high degree, it gets deleted, and the edges incident to it also gets deleted, so that a smaller graph is generated. And in the smaller graph, you solve for a smaller value of k, the same problem,
Yes, yes, I
and you
understood.
do it exhaustively. So like both of you have said that it can happen that once we delete some of the edges, then some vertices can become isolated. And for those vertices, the rule 1 will become applicable again. And therefore, that rule 1 should be implemented.
Yes, yes, yeah.
So as per this algorithm, you keep applying the reduction rules exhaustively as long as it is applicable. So, but once you have exhausted all the reduction rules and in the reduced graph, no more reduction rules are applicable, then if you see that the number of vertices is only k square plus k or less, and the number of edges is only k square or less, then you can be sure that the original graph that you started with is also an ES instance. So I think, uh, I made it G dash, but in the book it is saying G. So just give me one moment. Let me understand the proof once again. So the graph that we started with had n vertices. Okay, so as per my notation, so they didn't have this. I think this is correct only. Fine. So we started with a graph G, which had n vertices. But then after all the rules are applied, then we are left with G dash. In G dash, we should not have more than so many vertices for the instance to be an US instance.
Yes, yes.
So let us look at the proof, then we can argue. I will give the proof of this, then we can see if we have made a mistake or if there is any modification which is required. Okay, so first thing is, since we cannot apply rule 1 anymore, that means G does not have any isolated vertices. That is sure. G is devoid of any isolated vertices. I mean G dash for our purposes. For our purposes, that is first thing. And for every vertex cover S of G dash, every vertex of G minus S should be adjacent to some vertex from S. Since we cannot apply reduction 3, every vertex of G has degree at most k. Okay, so G dash, every vertex, let me write it down. So every vertex of G dash for all V in vertex of G dash, degree of V is at most k. So what does these two things imply? These two things imply that if S is a vertex cover of G dash, then after removal of S from G dash, so this is the vertex set. So this is by V of G dash minus S, I mean all these vertices which are other than the vertices in the vertex cover. So all these vertices are adjacent. So every vertex, and I should write it properly, every vertex in this thing is adjacent to some vertex in S. So each vertex in G dash is adjacent to some vertex in S. This is fine.
Yes.
What does it mean?
So this is the meaning of what is a vertex cover. So I'm saying that suppose that there is a vertex cover S of G dash, then every vertex which is not in S must be adjacent to some vertex in S. So, so,
Yes, yes.
so consider an edge. Suppose this is UV. I'm saying that U is in S. So either V is in S or V is adjacent to some vertex in S, because if none of the, okay, so S is a vertex cover, so G dash minus S, everything that is not in the vertex cover, that should be adjacent to, am I saying the right thing?
Yes, this is right. So all those vertices which are not the part of the vertex cover clearly would be the adjacent to an element of the vertex cover. Then only all the edges are going to be covered, because the vertex cover is covering all the edges. So yes,
Just give me 1 minute. So S is a vertex cover in G dash. So all these vertices are in the vertex cover. Okay, so now I'm looking at a vertex which is not in the vertex cover, but it is at the same time, let us say, not adjacent to any of the vertex cover vertices. Then it has to be isolated, but by assumption there is no isolated vertex. Okay, so because there is no isolated vertex, every vertex which is not in the vertex cover is connected to some vertex. If it is not connected to, since it has to be connected to some vertex, it must be connected to a vertex which is in the vertex cover. Otherwise, that edge will not be covered. Okay, so because of the reduction rule 1, this will be true because there is no isolated vertex. Yeah, now it is clear. So is it clear that because you don't have any isolated vertices, that is the reason I can say this?
Yes, yes. Yeah.
Yes. Okay. All right. So now, so this is, so if the size of the vertex cover is at most k, let us say, then what is the size of the graph? So how many vertices are there in the isolated graph? So that is equal to the number of vertices in S plus the number of vertices in G minus S, G dash minus S. Okay. So you know that this term is at most k. So now you know that the degree of every vertex in G dash is at most k. So that means every vertex in S would be adjacent to at most k vertices. So that means every vertex in S is able to cover at most k edges. Okay. So therefore, the number of vertices which are outside of S would be k times. So this term is at most k times k. I'll say it once again. Let me write it properly first. So I'll write it. This is less than equal to, this is k plus k times k. Okay. Okay. Why is that so? I'll say the argument again. So if S is a vertex cover of size at most k, then the number of vertices in S is at most k. That is clear. That is straightforward. Now you know that since there are no isolated vertices, every vertex which is not in the vertex cover is adjacent to some vertex cover in S. Okay. So then what is the total number of vertices which are not in the vertex cover? So you know that every vertex in the vertex cover S can be adjacent to at most k vertices outside the vertex cover. But in S, how many vertices are there? At most k. So therefore, k into k, at most k square vertices could be outside the vertex cover. So that is why this term is coming. So that is why
Ye-
the reduced graph has total so many vertices.
Yes, yes.
So is that clear, Rachana?
Yes, yes, it's clear.
Okay, thank you.
Also, this proves the number of edges is bounded by order k square.
Yes, 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 yes.
Yeah.
So because after the all the reduction rules are applied, so
Hmm.
every vertex in S could be
Yeah, it's
adjacent to
like
at
we are
most.
partitioning into a set S, and this G prime minus S is an independent set.
Yes, 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 yes. Yes. So is the number of pages being bounded by k square clear to you, Mr. Goel?
So number of vertices is clear to me, but I could
Okay.
not understand that why the number of the edges is bounded by the
Mhm.
k square, except this that this second term, the v g prime
Mhm.
minus s is an independent set. So these many edges would definitely exist.
Okay,
No, no, no.
fine.
Yeah. No, I made a wrong statement because this is an independent set. No, it is not an independent. This is independent of what? Independent set means that no edge exists in between, I mean, that set of the vertices. But however, so I could not understand that why the number of the edges is less than or equal is bounded by an amount of k square.
Okay. So you know that So you want to prove that if this is an yes instance, that means if G dash has a vertex cover of size k, then you want to prove this. Okay, so suppose that the vertex cover S is such that it has at most k members. So the vertex cover is having size at most k. So there are k vertices in the vertex cover which cover all the edges. So now you know that k vertices are sufficient to cover all the edges. But you know that each of these k vertices in the vertex cover has degree at most k. So
Yes.
how many edges could be there?
So for every vertex is having maximum k number of the edges.
Yes.
And then say, so k into k, the value came out to be k square.
Yes. Since every vertex is capable of covering only at most k edges, but all the edges are covered using at most k vertices only. So therefore, there cannot exist more than k into k edges in the
And
reduced
will
graph.
this, yeah, and will this bound be some tight bound? Because many edges are going to be reused here.
Yes, it is not tight. It is an upper bound only. It
Okay,
need not be tight.
okay.
But for some instances, it could be tight. But in general, it need not be tight. Maybe the number of edges is much smaller than k square.
Mhm. Yes,
So,
yes.
so it proves that if you have an ES instance, then you are just left with the job of counting how many vertices are there. And then, of course, you know that by brute force, you can enumerate what is the vertex cover of size at most so much. So this is not actually k, this is k dash. That means after you have done the reduction rules, the value of k has reduced. But this is this k is what it is called. So reusing a variable. So this is called abusing notation. So we have abused notation here. So in the original k that was, so original k means the original problem g and k. This k and this k are not same. This k is the k after you have done all the reductions, and in those rule 3 reductions, the k's value has been updated. So this is the updated k. This is not the original k. This is the updated k. But for the purpose of the simplicity of proving this lemma, we have reused or abused notation. Okay, so now we have seen that how kernelization can help us design and fixed parameter tractable algorithm for vertex cover. So we are done with the first part of our session today. So in the next part, which is very interesting, I will not go into very deep detail. So there is a paper. There is a paper we will discuss the result in this paper. I think we will not take more than half an hour. So this paper is in iCalc 2022 and in DCG also. Here there is a problem. I'll let you read the problem and then after some time we can discuss this paper. It does not use kernelization. So of course vertex cover is state textbook problem, but the problems in general could be complex, the real world problems, or rather uh, more interesting problems. So that would require more involved technique. So this is one of the simple to state problems that uses an FPT algorithm. So I will discuss this in uh, high level after some time. So we can come back at some after some time. So Rachana has a deadline hard stop at 5:30 or so. So I think we can come back. What time we shall come back? Like maybe 5:12 p.m. we can come back. Welcome back. So I hope that you had a chance to read the abstract. Okay, so let me ask you a simple question. So I'll give you two tasks. So, uh, so task one is you have a rectangle. So the rectangle's position is given to you. So you know the coordinates of the bottom left corner and the coordinates of the top right corner. So essentially, you know what is the length and breadth of the rectangle. And uh, the question is how many, let us say, unit radius disks can be packed within the rectangle non-overlappingly. For example, suppose, yeah, I don't know. Let's so we'll color it. Let us say this is unit radius disk. So disk means the circle along with the interior of the circle. So how many such disks can I place within the rectangle, but with the additional constraint that these disks should not have boundary overlap. Okay. The task 2 is similar. The task 2 is similar. Again, you have the same rectangle. You have been given one rectangle. And you are given additionally disks of different radii. The disks of different radii are given. So now you are allowed to have small and large, all kinds of disks you are allowed to have. You can ask the question is same, that what is the maximum disks number of disks that can be packed non-overlappingly within the rectangle. So now there are different radii. So the question, two tasks, the questions are clear.
Yes.
Yes, yes.
Okay. So the question, there are two tasks. So the question is, which task is harder? Harder in the sense takes more time.
I guess second one.
Yeah.
Second one, because we have been given disk of different sizes. So if
Mhm.
I try to use that, okay, the area covered by a smaller circle by a disk is a pi r square. So then I
Mhm.
take sum of the areas of all the disk, and I subtract this entire amount by an area of the rectangle, and then somehow I try to minimize the remaining space. But in the task 2, we can have the disk of the different sizes, so that would be difficult for me. However, but quite possible that by using the disk of the different sizes, I can use the smaller disk and then can minimize, can reduce the leftover area. Uh, yeah, that can be done.
So you're saying that in the first task, the sum of the areas of the disks is easy to calculate. But here also the sum of the disks, you know what are the radius of the disks, so you know what is the total sum of the disk. That is known to you.
Oh, I see. So if all the disks are known in advance, because I thought that we do not know the number of the disk in advance, and we have to find it out for the perfect packing of the disk in the given space. So if we know the disk, if we know the number of the disk and their sizes, then both the problems can be solved.
I'm not able to hear you. You're not audible. Hello. I, for some reason you were not audible. Is it that I am not able to hear, or
No,
but is not
I
able?
also cannot hear him.
Okay, okay. My connection is just fine.
Am I audible?
You were not audible for some time. I was trying to
Okay.
see if there's a problem with the connection.
Yes, there was a connection. At my end.
Yes, yes, yes. So I'm saying that in both the problems, you know that what are the disks to be packed. So here, let us say that you have an infinite supply of unit disks. Here you have some finite supply of disks, but you know what are the dimensions of the radius of the disks. Okay. So you have to maximize the number of disks that you can pack. So of course, you can start with the small disks, then you can go with the larger disks and so on you can do. But you have to also maintain that these disks are packed non-overlappingly. Okay, so turns out that this is NP hard. This task 2 is NP hard. So you cannot find in polynomial time what is the maximum number of disks that you can pack non-overlappingly within a rectangle. Okay, there is a paper, I think 2011 paper.
What about circle? What if I replace this rectangle by a circle and keep the problem statement same?
Okay, but I don't know.
This time I'm having a situation wherein I want to pack cricket balls, say inside a big football, such that the area is minimized. Or in fact, I'm looking for a perfect packing of the cricket balls inside the football.
So Rachana knows this. I think she's so in 3 dimensions she might have read something.
There are many conjectures again out there in 3 and higher dimensions.
Okay.
Yeah, but some of the packings are there which are, I don't know if they are known to be optimal, but they do provide a good packing.
Mhm. I'm somehow inclined to believe that since the problem is NP hard for rectangle, it would also be NP hard for circle,
Yeah.
but I do not know what is the answer. I'll find out and I'll let you know.
Okay.
But interestingly, this problem is not NP hard, or rather, is not known to be NP hard. So whether this is simpler or not, we don't know. So what they say is that the NP hardness status is unknown. I should say NP hardness status is not known. There is no proof this problem is hard. Okay. So, but we do not even know an algorithm that can find the maximum number of unit disks that you can pack within a rectangle. That is also surprising. Okay. So since this is such an elusive problem, in this paper they look at a different variant. So in this paper they are asking the following question: that look, you have been given a rectangle, there is a rectangle, but additionally you have been also given a packing of certain disks. So let me take some disk. So some packing is given. Let us say 3 disks are packed. I'm being, yeah, I mean, what I can do is, yeah, let's delete this, draw a few more disks. So a rectangle, and within the rectangle, given some disks. Okay. And the question is, can I relocate? Is the number. So two numbers k and h are given. And the question is it possible by relocating the positions of at most h disks to pack k additional disks? Okay. So can I relocate at most h disks from the packing to make space, or to be able to pack k additional disks? So you have two parameters. So two parameters k and h are there. And your objective is to design a fixed parameter tractable algorithm. So is the question clear?
Actually, this question is not clear. Can I relocate means what, and what's
Okay,
the
okay.
purpose?
So for example, so let me show you a concrete instance. Can I, so for example, so let us say that this was the initial packing. Let's take this. So you saw that there are 6 disks within this rectangle, and let us say k is 2 and h is also 2. So the question is, can I move around only 2 disks to make space? For example, can I move this guy and this guy downwards? So if I move these 2 guys downwards, so I make space here and there's already some space here. So I can add 2 additional disks here and here. So I want to, so for, let's do that. So this is my instance, and I'm going to do the relocation. So I'm going to move this disk and this disk around. So I would prefer, let us say that this is slightly to the right. Yeah. So let's, if these 2 disks were slightly to the, so let's say this is not here. So let us say this two, there was more space here. Let us say. This guy was here. This guy was here. So I can move around these 2 disks down. Let's do that. So I'm going to move, let's use a different color also. So I move this thing down. So since it has moved, I'm going to color it red. Okay, let's make it large. So I move this thing down, and the other one which was here, that also I'm moving down. That is called relocation. Yeah, so this was the case. Yeah. Yeah. Okay. So I'm going to give some names. So let us say this is A, B, C, D, E, F. So I have moved C and F. So C has come here, F has come here. A, B, C are D and E are in their original positions. So now I'm able to place two more disks here. So that is the meaning of relocation.
Yes, yes.
So the problem
And the
is,
value of, yeah, and the value of h and k could I mean maybe different.
yes, H and key need not be same. So H and K are part of the input. So earlier we have seen G comma K kind of inputs. So here we are looking at a geometric problem. So we are looking at a geometric problem. So our input is some geometric shapes plus, or not only shapes, geometric shapes and their positions. Additionally, you have these two parameters H and K, which need not be same. So you want to find the parameterized algorithm. So your running time should be function of H plus K times n to the power constant, where so what is n? What is the running time we have? Just a second. Let's look at the abstract once again. Yeah, so they have written what they want. So our main algorithmic contribution is an algorithm that solves a repacking problem in time h plus k to the power order h plus k. So this is the f of h plus k kind of thing, plus I to the power constant, where I is the input size. I would say that this is the, let us say, dimension of the rectangle. So how large, let's say, I is length of the rectangle plus breadth of the rectangle. So these are the kind of questions which are more complicated. So the reason why I posed this question, or I thought that I will give a high level idea for this problem, is because it is recent. People look at these kind of questions nowadays, and it does not use kernelization. But what it uses is very simple. So I'll give you, so this problem you want to get from here to here, and you want to do it in this kind of time. N is the dimension of the rectangle. Then what approaches one might think of? I'll give you a minute or two to give it a thought, and we'll discuss. This is our goal.
The input does not include the number of disks that we were given.
There is a, yeah, input also specifies the positions of the disks in the packing. It gives a packing. The goal is to repack so that at most k disks are relocated to make space for, oh no, so at most h disks are relocated so that additionally
K.
k disks can be packed. So k and h, and this packing, initial packing is given.
Okay.
Yes, so first we find the area of the rectangle and then we subtract the sum of the areas of the disk and whatever value we get. So first we'll check that whether k number of the disk can be accommodated in this, I mean, in this area or not. So say
In the
that
remaining
quantity,
space, yeah, that is true.
yes,
Huh.
yes. So then, yeah, so I would be writing the remaining area in terms of say pi x square or say pi r square. I mean, say k into sorry, say n into so something say t into pi r square. So it means that t.
R is 1, let us say radius is 1.
Okay, so then yeah, so then I will divide this the remaining space by the value of pi. So potentially these many disks can be included.
Yes, but then you have to also ensure that there is no overlap.
Yes. So now, yes. So, okay. So I need that space. I need to check. Okay. Yes. So this is just the initial screening that whether there is some leftover area in the or
Yes,
not.
that is the first filtering,
Yes.
the first level of check. Yes, that is of course, if there is not enough space to pack, then the question of packing non-overlappingly will not arise. The first check is how many disks can be packed at most. That's an upper bound. But then we have to refine and say that, okay, so many disks can be packed.
Yes. So then I divide this rectangle into the multiple number of the grids, and the size of the grid somehow should be equals to something. And by using those grids, I can determine the location of the new disk. So or we can see what is the the coordinates of the leftmost. What is the lowest coordinate, lowest value of the x coordinate, and the lowest value of the y coordinate, kind of the thing, after dividing this entire region into the grids, so that I can identify that yeah, what could be the maximum size of the leftover space, maximum
So,
coordinate of the leftover space. Yes.
so you are dividing the rectangle, let us say, into two parts.
Not
You
into the two parts. I mean the number. So yeah, I should take the given radius into the consideration. So I would be dividing into the grid of the size 1 cross 1, say each. That,
okay? So you divide, you overlay a grid of 1 cross 1 dimension on the rectangle.
yes, yes. And from here, probably I can then find one empty square in the leftmost side, or in the upper side, or in the rightmost side. That will give me a tentative, estimate
Okay.
of
So you're
of
saying that if any of the grid cells is empty, you can place one of the
yes,
additional
yes,
disks.
yes, yes,
But it may happen that none of the grid cells are empty. Then you have to resort to relocation of some of the disks. So that problem will arise.
yes,
So we can see that the problem is not trivial at all. It's quite complicated. And but the good thing is they reduce the problem to the knapsack, weighted knapsack problem. So in the weighted knapsack problem, there is a knapsack or bag of size weight, and items are to be packed. So this is item 1, item 2, and so on. So items have values, so value v1 and so on. So you want to pack the items. So this is 0 on knapsack packing. So you cannot take partial items. You either take an item or you don't take an item. So in the knapsack problem, the question is which items you should pick to be included into the bag or knapsack so that the value of the bag is maximized. And the bag volume is not overflown. I mean, so you don't pick more than the size of the bag. So the total weight of items taken is less than W. So they reduce the problem to the knapsack problem. That is the beauty. So I want to finish early. In the next 5-10 minutes, I will tell you what they do. Okay. So let's look at it. Quite difficult. Huh. So the first step is what they call identifying the free areas. So which areas are relatively free? So there is no space here, so that cannot be considered free. So which areas are relatively free? So they identify free areas. Okay. So that is the first step. I'll write down. Identify the free areas. They have criteria of what is a free area. Free areas are also called holes. Okay, that's the first part. And then holes could be sort of independent of each other. So you can focus on one hole at a time. Okay, so in one hole, how many new disks can be added? You can ask, and that may be independent of filling the other hole. So that filling of the holes by adding new disks, it is done greedily. So they have a greedy algorithm. So there's a greedy algorithm for filling the holes. I'm giving a high level idea only. Okay. And then what they do, so they have to bring in the fixed parameter tractability. So they have to bring in H and K somehow. So to do that, they look at the packing. So this is the packing, and they use two different colors, red and blue, to color the discs of the packing. Okay, so they're going to color. There's a color coding step. I'll write down. There's a color coding step. Maybe I should have said this before. So in the color coding step, they color the existing discs blue and red. So what is the meaning of blue and red? I'll tell you. This is red and this is blue. So some of these things are made blue, let us say. So if I say that C and F I have moved, so if I make this blue, these two blue, blue means that this is a potential candidate for relocation. Okay, so this can be moved. This can be moved, and red means that its position is going to be fixed in my final solution. Okay, so now the question is, how do you decide that which disk you will make blue and which disk you will make red? Okay, so you have one thing up to, so you know that, so it is known that at most H disks can be relocated, and at least K disks are to be added. K additional disk, extra disks are to be packed. Okay, so now they're able to do this guess that which of these given disks, you know that which are the disks. And okay, so n could potentially mean the number of disks in the packing plus the dimension of the rectangle. So probably there are n disks in the original packing. So out of that, you want to color at most k disks, h disks blue. So in how many ways you can do that? So n disks, h disks are to be colored blue. In how many ways you can color h disks blue?
So number of, yeah.
Yeah, so you were saying something?
Juice,
Yes, yes, yes. So the dependence on n is a problem. That is a problem. So you want to have a running time, which is, so for example, if you have n choose h, then your running time is n to the power h. That you don't want. You don't want that kind of running time. You would prefer to have a running time which is order h plus k to the order h plus k into n to the power constant. So Okay, they are saying I am saying N. So here they are doing some very clever things. So they have a clever guessing strategy. So they have a clever guessing strategy, and this is beyond the scope of this discussion. But with that clever guessing strategy, they're able to achieve a running time of this to guess. So once the guessing is done, then the knapsack will come. So once the guessing is done, then they know that, okay, so for example, suppose you have fixed that which H disks are to be relocated. So now you relocate them, but the relocations, there are infinite ways to relocate things. So you can move things around. There's a continuous, which direction you will move, all these things are sort of, there are many choices. So now they have some greedy rule with which they do this relocation and some heuristics. So after that, they are able to sort of maximize the free space in each. So the holes, they are able to maximize the holes. Now each of these holes, they call it the set of holes, they call it container. So each container is is becoming a knapsack. Okay. Now within the knapsack, okay, so how, now I'll tell you that once what is the first step, that you identify this potential disk that can be relocated, and when you identify, or rather decide in which direction and in which way they have to move, then you sort of maximize the area of the holes. So once the containers or holes you have identified, the next step is to uh, cast this problem as a variant of the knapsack problem. So what they do in the knapsack problem is that the weight of the knapsack becomes the weight of a hole. The weight of a hole is the number of existing disks that need to be relocated in the hole. So relocation is a cost. So you know that within the container there are some of these blue disks. So these blue disks you are free to relocate. So if there are more blue disks, then you have sort of more liberty to move things around. So that is the weight of the container, and value of an item. It is the value of the container is the total number of disks. Final value of the container means the whole. The value of the knapsack is the value of the total number of disks, both relocated and new, means newly added, that can be packed within the whole. Of course, non-overlappingly. And I'll give you 1 or 2 minutes to think about how the problem has sort of changed from this domain of packing disks into rectangles into this knapsack problem.
So, what is the knapsack here? Is a whole
Yeah,
away.
so whole means some free space.
Hmm.
So that is the knapsack where you want to fit in the items, and the
Yes.
items are these disks.
So, if the items are disks, then when we consider the value,
Hmm.
like in a standard knapsack problem, we want to we are given the values of items.
Yeah, so when I say value here, I'm saying that the value of the knapsack, final value of the knapsack. So yeah, so those values. So value of each item is 1. You can think of that,
Okay.
and the value of knapsack is the total number of
Oh, right. So we want to maximize this value.
yes, the
Okay.
total number of disks within the hole.
Correct.
That
Correct.
yes. So the thing is, you know that the problem cannot be solved within the rectangle. Then how
Hmm.
do you solve this? So this is nothing but a sub problem. That
Yes. Yes.
now instead of packing disks within the rectangle, I am packing disks within a small space.
Hmm.
To solve that, they have a module, and
Hmm.
in that module, so what they do is the following. So they have generated some equations. So they solve some equations.
Hmm.
Okay, so I'll tell you what they do. So they have to maintain the. So let us say this is some hole. This is a.
Hmm.
So means generally you would prefer the holes to be rectangular. So they have done some approximation and other things. So then they have to ensure the non-overlapping condition. So what they do that, okay. So consider two disks, I and J. If these two disks are non-overlappingly placed within the hole, let us say this is I,
Hmm.
this is J,
Hmm.
then that means that their centers must be at least two distance apart.
Yes.
So they ensure that, let us say this is, so one center is Xi, let us say this is one center, the other center is this one. So they
Yes.
ensure that, okay, so Xi minus Xj squared plus Yi minus Yj squared, this is at least 4.
Right.
So so they generate certain equations that, okay,
Hmm.
so then this is one condition, non-overlapping. The other condition is the boundary condition, that, okay, so the disk should be within the boundary of the hole.
Right.
So to do so so generally, so they have some approximations of the hole into rectangles. So they
Hmm.
know that, okay, so I have to fill in the disks within some x minimum to some x maximum,
Hmm.
and some y minimum to some y maximum. Then there's a, so each disk should be so each disk's center should be between x max minus 1 and
Yes. Yes.
x mean
X
plus
min
1.
plus one
Similarly,
for the
y
y
max,
coordinates.
yes. So they are able to show that this equations, this polynomial equations
Hmm.
is solvable,
Okay.
and then they solve it, and of course there are more intricacies, but somehow reducing the problem into some smaller problem, they're able to handle it. And then once it is the knapsack problem, the knapsack problem has a FPT algorithm, so the dynamic programming algorithm, uh,
Yes.
where you have the items, the rows are corresponding to the items, one, two, and these are the weights. So the maximum weight of the knapsack is W. So the ijth entry is saying that if you include only the first I items, then
Hmm.
uh, if you also insist that you don't pack more than J weight, then what is the maximum
Maximum
value you
value.
can get?
Hmm.
So that running time is sort of n omega NW. Oh, no, no. Is it
Yeah, I think
NW?
it's ending. Yes. Yeah. Or
Ye-
something.
Yes.
How
So
time does it take to? That is the table size.
Uh, yes. So we have to pack n
n
but then
items.
W, yeah, but W here is exponential thing actually.
Yes, yes, yes. So W is the size of the rectangle, which is or knapsack, which is uh, so we are hoping for a running time which is h plus k to the power h plus k into n to the power constant. So n is the size of the rectangle, or the plus the number of disks in the initial packing. So for our purposes, W is a given variable, and it is not exponential.
Yes.
So this was a high level overview. I don't know if it was possible to say anything more detailed, but I thought that yeah, this is an algorithm which requires so many other things other than kernelization, which we have not seen in the course. But I do not expect you to understand. I myself don't understand all the things, but it was a high level thing. So if you have any questions, you can ask, or we can
So this
discuss
paper,
anything.
so this paper took complete 2 years to get accepted from 2022 to 2024.
It was accepted in a conference in 22. Then people are lazy. Once they will send it to the journal, so the journal takes 1.5 years or its own time. So in journal, the timeline of 2 years is like quite average or expected only.
Okay,
But the dissemination of knowledge takes place once you publish it in the conference, which happened in 22.
okay.
Okay, I think I have taken a lot of time. I thought that I will finish early. So this is officially the end of this course from my side. I thank Mr. Goel for being regular and also Rachana for coming today. And if there is anything, you can always contact me. And Mr. Goel, if you have time in your free time, fill 1 or 2 feedback forms. That is sort of formality helps me.
Sure, sure. Continuously, I've been filling the feedback forms.
Oh, okay, okay. That is great. I am not able to see it. I will be able to see it only after the exams are over.
Okay, okay, yes.
Okay.
So I'll fill the remaining ones also. Yeah,
No,
definitely.
if you don't have to fill more than 5 or 6, that is sufficient.
And thank
Yes,
you
yes.
so very much for making Herculean efforts, and you made tremendous effort. I mean, throughout the semester, and I thoroughly enjoyed your session. So whenever you take TA shape in the next semester, I mean, please do let me know. Yeah.
Yes, yes, yes. It's a pleasure to have you in the audience.
Thank you so very much.
Yes, yes.
Thanks, it. Bye bye.
Okay.
Have a
All
nice
right.
day.
Take care. Take care.
Bye.
All right, Rachana. Bye.
Yeah, bye bye. Thank you.
Yes, yes. Prabhnur is also there. Bye, Prabhnur. Thanks for coming.